Hi everyone! This is Professor M. Science, and today I want to build the energy eigenvalues and eigenfunctions of the hydrogen atom in another one of our videos on rigorous quantum mechanics. Hydrogen is one of the very few systems for which we can solve the equations of quantum mechanics analytically. You can find the full mathematical solution in our companion video. What we will do today is to take that mathematical solution of the hydrogen atom and to build the first few eigenvalues and eigenfunctions to see what they look like. Let's go!
The hydrogen atom is made of two particles, a proton and an electron. We know from the introductory video on hydrogen that the center of mass of the atom moves freely, and it is trivial to describe it in quantum mechanics. The relevant physics of the system is encoded by the relative motion of the proton and the electron, and we describe the hydrogen atom with a one-particle relative Hamiltonian that we call H subindex rel for relative. The Hamiltonian has a kinetic energy term and a potential energy term. We derived this relative Hamiltonian in the introductory video on the hydrogen atom, and as a reminder, mu here is the reduced mass of the system and is related to the masses of the proton and electron by this equation. P here is the relative momentum given by this expression in terms of the individual momenta of the proton and electron, and R here is the relative position given by the distance between the proton and the electron. For convenience, in today's video, we will work in the position representation. So we can rewrite the relative Hamiltonian as equal to the kinetic energy term in the position representation plus the potential energy term in the position representation. An important feature of this Hamiltonian is that the potential is a central potential. And that means that all the results associated with central potentials will apply in the case of hydrogen. This relative Hamiltonian is really the key to understanding the hydrogen atom using quantum mechanics, and in this video we will calculate a few of its eigenvalues and eigenfunctions. Moving forward, we're going to simplify notation and we'll just drop the rel subindex, and we will simply write H for the relative Hamiltonian, but now you know what we're referring to. Okay, so the eigenvalue equation of the Hamiltonian takes the usual form, where these are the eigenvalues and these are the eigenfunctions. The full mathematical solution of this eigenvalue equation is rather involved, but I would say it's also rather interesting because after some manipulation you end up with a nice power series expansion, which maybe is not something you expected. We've gone through the mathematical derivation step by step in a companion video that is linked in the description, so we're not going to repeat it today, but you can check out the link if you want to know more details. What we will do today is to just take that solution as a given, and we will use it to calculate eigenvalues and eigenfunctions. So the first thing we need is a quick recap of the mathematical solution to use as a starting point. The first step is to realize that the hydrogen atom Hamiltonian commutes with orbital angular momentum. This means that the eigenfunctions of the Hamiltonian can be chosen to also be eigenfunctions of the squared orbital angular momentum like this. And remember that the quantum number L can take any non-negative integer value. The eigenfunctions can be chosen to also be eigenfunctions of the Lz orbital angular momentum, like this. And again, remember that for a given L, ML can only take one of these values separated by integer steps. From these results, we can rewrite the eigenvalue equation for the Hamiltonian, where we label the eigenfunctions and eigenvalues with the appropriate quantum numbers like this. We see that the eigenfunctions depend on the orbital angular momentum quantum numbers L and ml, and for every combination L-ml, we have a spectrum of energy eigenfunctions labelled by the additional quantum number k. In principle, the energy eigenvalues can also be labelled by these three quantum numbers, but we find in the videos on central potentials that they actually only depend on k and l, but not on ml. All we've done so far is to simply rewrite the eigenvalue equation of the Hamiltonian using the appropriate quantum numbers for the eigenvalues and eigenfunctions. That means that we're now ready for a quick recap of the mathematical solution. The full eigenfunction psi is given by the product of a radial part and an angular part. This angular part here is the same for any central potential and is given by the spherical harmonics, which are the orbital angular momentum eigenfunctions and only depend on the quantum numbers L and ML. We have a whole series of videos on orbital angular momentum and spherical harmonics, and we will use those results for building the angular part of the hydrogen atom eigenfunctions. So moving to the radial part here, its form depends on the precise form of the radial potential, but it is always labelled by the quantum numbers K and L. Figuring out the radial part takes a rather large number of steps, but luckily for us, we've already done that in our companion mathematical video. So first, we rewrite the radial function in terms of a new function u like this. We then make a change of variables to rewrite u as a function of a new variable ρ. Rho is a ratio of r and the reduced Bohr radius. And the reduced Bohr radius is given by this expression. Okay, next, by considering the limit of large ρ, we rewrite u in terms of yet another function v, like this. In this expression, lambda is defined as equal to the square root of minus the eigenvalue over the ionization energy, where the ionization energy is given by this expression. Next, we express the function v in a power series like this, where the exponent s is equal to L plus 1. The expansion coefficient CQ is related to the expansion coefficient C0 by this rather long expression. And this is true for Q smaller than K. The expansion coefficient CQ vanishes if Q is larger than or equal to K. These expansion coefficients imply that the power series is finite. And we then complete the solution by fixing C0 through normalizing the wave function. This here is the strategy that we will follow in this video to build the eigenfunctions. First, we will determine what these C expansion coefficients are for a given choice of quantum numbers K and L. We will then use them to construct phi. Then we will build u in terms of the ρ variable. We'll then go back to the original coordinate r. And once we have u like this, we will construct the radial function. And once we have r, we will finally build the eigenfunctions. With this recipe, we can build any eigenfunction we want. And in this video, we look at a few examples of how to do it explicitly, and we're going to do it step by step. Before we do any of that though, we should clarify that the discussion today corresponds to the non-relativistic hydrogen atom. So we're not going to consider topics such as spin, fine structure, or hyperfine structure, which have important consequences for the hydrogen atom, eigenvalues, and eigenfunctions, but which we're going to leave for other videos, so stay tuned for those. As we just discussed, we need to normalize the eigenfunctions to fix the C0 expansion coefficient. The full wave function obeys the standard normalization condition, so we could fix C0 by imposing this condition. However, in the videos on central potentials, we discussed that we can separately normalize the radial part of the eigenfunction and the angular part of the eigenfunction. Indeed, we have already built the spherical harmonics such that they are normalized. So in principle, we can fix C0 by using this normalization condition for the radial part of the eigenfunction. But in the video on the radial equation, we find that we can equivalently normalize the u function using this relation. The original normalization of the radial function involves the r squared here, but the normalization in terms of the u function doesn't, so this expression is in general simpler, and today we will normalize the wave function and fix C0 using this u integral. We need one final piece of recap around the eigenvalues. The eigenvalues are in principle labelled by the indices k and l, and given by minus the ionization energy over k plus l squared. Remember from the companion mathematical video that we are only considering bound states of the hydrogen atom for which the eigenvalues are negative as the potential is 0 at infinity. From this expression, we see that k and l only appear together as a sum here, which suggests that we can define a new collective label n. In terms of this new label, we can write the eigenvalues E sub n as equal to minus the ionization energy over n squared. Remembering the expression for the ionization energy that we had earlier, we can rewrite this expression in terms of the reduced mass and the electron charge on the numerator, and this constant multiplying the squares of the vacuum permittivity, the reduced Planck constant, and the label n. If we use the label n for the eigenvalues, we need to figure out what are its allowed values. We know that the angular momentum quantum number L can take non-negative integer values. And we also know from the companion mathematical video that k can only take positive integer values. From these, we can conclude that n, which is equal to k plus l, can only take positive integer values. But we can actually say more, starting from the fact that n is equal to k plus l. Let's start with the lowest possible n, which is equal to 1. This will correspond to the lowest energy, so to the ground state of the hydrogen atom, and the only possible values are k equals 1 and l equals 0. For the first excited state, we have n equals 2. We now have two possibilities, either k equals 2 and l equals 0, or k equals 1 and l equals 1. And both options give the same n and therefore the same energy. For n equals 3, we now have three options, either k equals 3 and l equals 0, or k equals 2 and l equals 1, or k equals 1 and l equals 2. And we could, of course, continue in this fashion for any n. Now, if we use n as a quantum number for the eigenvalues, then it would also make sense to use n as a quantum number for the eigenfunctions. This means that we can either label the eigenfunctions with the quantum numbers k, l, and ml like this, or with the quantum numbers n, l, and ml like this. This second option is the most common, but we will make sure that we clarify the relation between the two throughout this video. And we're now ready to build the first few eigenvalues and eigenfunctions of the hydrogen atom. Let's start with the ground state, which is n equals 1. If we look at the general expression for the eigenenergies up here, we get that the ground state energy is equal to minus the ionization energy. We can also explicitly write out the ionization energy in terms of the reduced mass of the system and fundamental constants like this. Sticking with the ground state, let's now turn to the eigenfunctions. The first thing to remember is that for n equals 1, we've just established that k is 1 and that l is 0. To build the eigenfunctions, we now have to follow the recipe that we discussed earlier, where the first step is to determine the expansion coefficients using the expression up here. And as k equals 1 and the expansion coefficients vanish for any q larger than or equal to k as shown here, then we can conclude that the only non-zero expansion coefficient is c0. To put it another way, the ground state eigenfunctions have a single term in the power series expansion. The next step is to build V. For the ground state, k equals 1 and l equals 0, so that we write V with the subindices 1, 0. Next, as we've just established that all expansion coefficients are 0 apart from the first one, which corresponds to q equals 0, then this expansion up here has a single term, which we can write down explicitly. As s is equal to l plus 1, but l is 0, then the power of rho is simply 1. This means that we can get that v subindex 10 is equal to C0 times rho. Right, the next step is to build U. In the ground state, this is U10. Inserting the expression for V inside this equation, we get C0 times rho times this exponential. Now we quickly remind ourselves of the definition of lambda, and in our case we have lambda 10, which is equal to this square root. Using the fact that the ground state energy is equal to minus the ionization energy, we get that lambda equals 1. Going back to our expression for U, we get that it is equal to C0 times rho times the exponential of minus rho. At this point, we can go back from rho to r using this relation, and we can write the U function in terms of r as equal to this. Now that we have the U function, we can normalize it to fix C0. Rewriting the normalization condition for the ground state, we get this. Using the expression for U10 up here, we end up with this new integral. And we're now going to use a standard exponential integral, which you can look up in your favorite table of integrals or actually evaluate it yourself, and it is equal to this. Comparing this exponent with our exponent up here, we can identify p as equal to 2. And this exponent with this exponent, we get alpha as equal to 2 over a0. For the integral, we first get the absolute value squared of c0 over a0 squared, and we can then use the standard integral to get 2 factorial over 2 over a0 all cubed. Simplifying, we get the absolute value squared of c0 multiplying a0 over 4. We can then isolate c0 and get 2 over the square root of a0. And by the way, I have made a phase choice such that we end up with a real positive constant. With this result, we can rewrite U10 as equal to this prefactor times r times the exponential. Okay, we are almost done. The next step is to go to the original radial function. In the ground state, this is r10. Inserting the expression for u inside this equation, we get the prefactor times the exponential. Finally, the full eigenfunction is given by the product of the radial function and the corresponding spherical harmonic. In our case, as L equals 0, then ML only has one possible value, which is also 0. Using the results from the video on spherical harmonics, y00 is equal to 1 over the square root of 4 pi. We can insert this expression for the spherical harmonic all the way up here, and this expression we just found for the radial function into this term. With this, we get the ground state wave function using the KL-ML quantum numbers, and we end up with the ground state wave function of the hydrogen atom as equal to this prefactor times this exponential. If we instead use the NL-ML notation, in this particular case, the ground state is also labelled as psi 100, and of course it's given by the same expression. It is great to have this mathematical expression for the ground state eigenfunction, but it would be helpful to also visualize it. Unfortunately, we cannot fully visualize it because it depends on 3 coordinates, which means that we would need a 4-dimensional space to draw it fully. And what we will do instead is to separately visualize the radial part and the angular part. This is a depiction of the ground state wave function of the hydrogen atom. The radial part on the left shows that the eigenfunction decreases exponentially as we move away from the origin of the potential. The angular part on the right here, is an eigenstate of orbital angular momentum, and in this particular case, it is the y00 spherical harmonic, which is simply a constant. If you need a refresher on how to draw spherical harmonics, check out the corresponding video, we've linked it in the description. In general, they depend on the angular variables theta and phi, so we can draw them on the unit sphere, and we use a red, white, blue color gradient scale with red representing positive, white is 0 and blue is negative. In this case, we get a uniform red sphere because the y00 spherical harmonic is a positive constant. Overall, the ground state eigenfunction of hydrogen takes its maximum value at the origin of the potential and then decays away from the origin and does so isotropically. The ground state of the hydrogen atom has an iconic place in physics and in chemistry, and we have a video exclusively dedicated to exploring in more depth the physical meaning of this ground state eigenfunction. So I encourage you to follow the link in the description to check it out. But for now, let's go on and construct some excited state eigenvalues and eigenfunctions. Let's now move to the first excited state. The procedure is analogous to what we just did for the ground state, so we're going to go quicker through the calculations, but I encourage you to fill in the gaps. Let's start again with the eigenvalues and let's consider n equals 2. The energy E2 of the first excited state is equal to minus the ionization energy over 4. Let's now turn to the eigenfunctions. Remembering that for n equals 2 we have two possibilities. We can have k equals 2 and L equals 0, or we can have k equals 1 and L equals 1. So let's first focus on this top case. From the expression CQ at the top, we see that the non-zero expansion coefficients are those for which Q is smaller than K. As we have K equals 2, we can conclude that we have two non-zero expansion coefficients, C0 and C1. Using the expression in the first line at the top here, we can plug in the values Q equals 1, K equals 2 and L equals 0 to write C1 as equal to this long expression. And it trivially evaluates 2 minus C0 over 2. So, the power series has two non-zero expansion coefficients, C0 here and C1 here, which we can write in terms of C0 like this. The next step is to build V. Remembering that we're working with this combination of K and L, we have V20. We've just established that we have two terms in the power series, one corresponding to Q equals 0 and one corresponding to Q equals 1. As S is equal to L plus 1 and L is 0, we can conclude that S equals 1. And we can then rewrite V as the sum over these two terms. Finally, remember that we've just established that C1 is equal to minus C0 over 2. So taking C0 as a common factor here, we end up with this expression. In summary, the function V20 takes this form. The next step is to build U20. We can insert this expression we just found for V20 into this expression and get this polynomial term times the exponential. For the exponential, we need to determine lambda, which, remember, is given by this expression. In our case, we have lambda 20, which is equal to this square root. Using the fact that the energy is equal to minus the ionization energy divided by 4, we get that lambda equals 1/2. And this implies that U is equal to C0 times this polynomial in rho times this exponential of minus rho over 2. At this point, we can go back from rho to R using this relation, and we can write the U function in terms of R as equal to this. We again determine C0 by normalizing the function U, and we have this normalization integral. Inserting the expression for U20 into the normalization condition, we first get the absolute value squared of C0, and then the integral has three terms in the integrand arising from the square of the polynomial featuring in U20. Feel free to pause here to cross-check this step. Each of the terms in the integrand is a power of r times an exponential, so we can again use the same standard exponential integral to evaluate each term, which remember is given by this expression. Now I'm going to skip a few manipulations which I encourage you to fill in, and this is what we get. Rearranging, we get that C0 is equal to 1 over square root of 2a0, where I have again made a phase choice such that we end up with a real positive constant. With this result, we can rewrite u20 as equal to this prefactor times this polynomial in R times the exponential. The next step is to go to the original radial function, which in our case is R20. Inserting the expression for u inside this equation, we get this prefactor times this polynomial times this exponential. Finally, the full eigenfunction is given by the product of the radial function and the corresponding spherical harmonic. As L equals 0, we again have ML equals 0, and the spherical harmonic is again y0, 0, and equal to 1 over the square root of 4 pi. So if we use the KLML notation, the overall eigenfunction of this first excited state is given by this expression. Using the NLM notation, in this particular case, we also have psi200 for the first excited state, and of course we have the same explicit expression. We will come back to this eigenfunction to visualize it in a moment, but before we do that, let's construct the other possible first excited states. Going back to the starting point of the first excited state eigenfunctions, which remember are given by n equals 2, we're now going to focus on this second possible combination of k and l. As k equals 1, then from this condition on Q here, we can conclude that all expansion coefficients apart from C0 vanish. The next step is to build V. Remembering that we are working with this combination of k and l, we have V11. We've just established that we have a single term in the pair series, the one corresponding to q equals 0, so we get this single term. As s is equal to l plus 1, we get this. And as l is equal to 1, we can rewrite V like this. Overall, V11 is equal to C0 times rho squared. The next step is to build U11. So inserting this expression we just got for V into this equation, we get C0 rho squared times this exponential. We are still working with the first excited state, so lambda 11 is the same that we got earlier for lambda 20, which is equal to 1/2. And that implies that u is equal to C0 times rho squared times the exponential of minus rho over 2. And we can now go back from rho to r using this relation, and we can write the u function in terms of r as equal to this. We now move to normalizing the function u to determine C0. Inserting the expression we have for u into the normalization integral, we get this integral. We can use the same standard exponential integral that we've been using throughout, and skipping a few steps, we end up with this. Rearranging, we get that C0 is equal to 1 over square root of 24a0, where, as usual, we choose a phase such that we end up with a real positive constant. And this all means that we can rewrite u11 as equal to this prefactor times this term proportional to r squared times the exponential. The next step is to go to the original radial function, which in our case is r11. Inserting the expression for u inside this equation, we get the prefactor times a term proportional to r times the exponential. Finally, the full eigenfunction is given by the product of the radial function and the corresponding spherical harmonic. As L equals 1, then ML has 3 possible values, -1, 0, and 1. Using the results from the video on spherical harmonics, we have that y1 minus 1 is equal to this expression, y10 is equal to this expression, and y11 is equal to this other expression. This leads to 3 distinct eigenfunctions, and we are going to start with the KL-ML labels as shown up here. The first one is psi11 minus 1 and is given by this combined prefactor, the R-dependent terms, and the angular dependent terms. The second one is psi110 and is given by this combined prefactor, the R-dependent terms, and the angular term. And the third is psi111, given by this other combined prefactor, the R-dependent terms, and the angular terms. Using the NLM notation, these 3 eigenfunctions are labelled as psi21 minus 1, psi210, and psi211. Right, so we can now bring together all the results for the first excited state, and we end up with 4 distinct eigenfunctions. Using the NLM notation, the first eigenfunction corresponds to 2, 0, 0, and is psi200. It is equal to this radial function and this angular function, and explicitly written like this. The next 3 eigenfunctions correspond to quantum numbers 21 minus 1 giving psi21 minus 1, 210 giving psi210, and 211 giving psi211. They all have the same radial parts here, here, and here. The angular parts, however, differ, with the y1 minus 1 spherical harmonic for the first one, the y10 spherical harmonic for the second one, and the y11 spherical harmonic for the third one. Explicitly, we get this for psi21 minus 1, this for psi210, and this for psi211. These results show that the radial function is the same for a given angular momentum L quantum number, but different between different values of L, with L equals 0 here and L equals 1 in these 3 cases here, here, and here. Overall, the first excited state of the hydrogen atom is, therefore, 4-fold degenerate. Let's now plot the first excited state eigenfunctions. First of all, I'm showing the radial parts, and I am using the NL-ML notation, so I hope that this is not too confusing compared to the original derivations where we were using the KL-ML notation. The figure on the left corresponds to the L equals 0 radial function. Like the ground state radial function, it has a positive value at the origin and then decays away from it. However, unlike the ground state radial function, this radial function has a node where it vanishes and then becomes negative. Finally, it approaches 0 again from below. The figure on the right corresponds to the L equals 1 radial function, which, remember, corresponds to 3 distinct eigenfunctions, 1 for each possible ML value. It is 0 at the origin, grows to a maximum value, and then decreases towards 0 as we move away from the origin. Bringing in the angular parts, we start with psi200, which, like the ground state, is isotropic. For psi21 minus 1, we get these radial and angular parts. And for ease of visualization, we can make the diagram of the spherical harmonic rotate like this. The y1 minus 1 spherical harmonic is a complex function, and we are plotting both its real and its imaginary parts. And again, if you need a refresher about how we plot the spherical harmonics, you can check out the corresponding video linked in the description. For psi210, we get these radial and angular parts. And in this case, the spherical harmonic is a real function that is spherically symmetric. For psi211, we get these radial and angular parts, and we can again make the y11 spherical harmonic rotate. We could repeat the same exercise for any other eigenfunction, but now that you've seen how it works for the ground state and first excited state, you will be able to calculate the eigenfunctions for any other state yourself. To encourage you to explore this further, I will finish the video by showing the results for the second excited state corresponding to n equals 3. The energy of the second excited state is equal to minus the ionization energy over 9. And we've seen earlier in the video that there are now 3 possible choices of K and L that give n equals 3. The first possibility is K equals 3 and L equals 0. This corresponds to n equals 3 and L equals 0. This leads to a single eigenfunction, which in the NL-ML notation is psi 300. The second possibility is K equals 2 and L equals 1. Or equivalently, n equals 3 and L equals 1. We have 3 eigenfunctions, which again using NL-ML notation are psi 31 minus 1, psi 310, and psi 311. And the third possibility is K equals 1 and L equals 2, or n equals 3 and L equals 2. And this leads to 5 eigenfunctions, which in NL-ML notation are psi 32 minus 2, psi 32 minus 1, psi 320, psi 321, and psi 322. I'm now showing the plots of the radial functions associated with the second excited state. The plot at the top corresponds to the case when L equals 0. In this case, the series solution has 3 terms leading to this expression for the radial function. The radial function starts as a positive value and decays away as we move away from the origin with 2 nodes here and here. This radial function corresponds to a single eigenfunction associated with the L equals 0 spherical harmonic. The figure in the middle corresponds to the case when L equals 1. In this case, the series solution has 2 terms leading to this radial function. The radial function starts at 0, then grows to a maximum, then decreases, crosses 0, reaches a minimum, and then approaches 0 from below as we move away from the origin. This radial function corresponds to 3 distinct eigenfunctions whose angular part is given by the L equals 1 spherical harmonics. The figure at the bottom corresponds to the case when L equals 2. In this case, the series solution has a single term that leads to this expression. The radial function starts at 0, grows to a maximum, and decreases to 0 as we move away from the origin. This radial function corresponds to 5 distinct eigenfunctions whose angular part is given by the L equals 2 spherical harmonics. Overall, these results indicate that the second excited state is 9-fold degenerate.
Today we have explicitly built and visualized the energy eigenvalues and eigenfunctions of hydrogen. To learn more about both, I would encourage you to check out the subsequent videos in our series on the hydrogen atom. These videos will include a detailed study of the ground state, as well as the emission spectrum of the hydrogen atom. And as always, if you liked the video, please subscribe.